Hello, this is Daniel. So far, we have discussed the classification algorithms that predict the class of newly observed data. In this video, we'll talk about linear regression, which predicts the class of continuous values. The presentation slides and source codes I use here were obtained from the Intel Machine Learning course. I reorganized the contents for easy understanding. You can download the original content from the website using the link. Then, let's get started. Here's a scatter plot of various movies. The x-axis represents the budgets, and the y-axis represents the box office revenue. Let's predict the box office revenue of a new movie using the input budget. In linear regression, we try to find a line of y equals beta 0 plus beta 1 times x that best represents this dataset. Our target or dependent variable, y, is box office revenue. The input independent variable is the movie budget. Beta 0 and beta 1 are coefficients. Beta 1 is the slope, and beta 0 is the intercept. Thus, finding a line means finding the best coefficients, beta 0 and beta 1. Suppose this blue line is the best line where beta 0 is 80 million and beta 1 is 0.6. With this line, we can predict the box office revenue for a new movie. If our budget is 160 million, we can earn 175 million in revenue. Let's calculate how accurate it is. We have predicted y values on the line and the actual truth from the training set, y coordinate of the red input point for a given line. This is the error formula for a given observation. We call the difference between predicted y and observed y as a residual. We usually take a square for a residual to make the difference a positive value. We calculate the minimum mean squared error for various coefficient values. The mean squared error, MSE, equation gives us the average residual error, where m is the number of input data. In other words, we want to find the coefficients that minimize the mean squared error or mean squared residuals. Then we can obtain the best line. The cost function is often written like this, equivalent to the previous function. J is a function of beta 0 and beta 1. In the denominator of the right side, we use 2m instead of m because it is convenient to solve the equation mathematically. We will discuss this part in a later video. Now let's compare the linear regression and KNNs. Model training is slow for linear regression, since we have to search for the best parameters. In contrast, KNNs are very fast to fit, since it's just storing the data. However, once the model is fit, linear regression is superior. It maintains just a few parameters, coefficients for the line. On the other hand, KNN needs to remember all the points, so it is memory intensive. Moreover, predictions for linear regression is very fast just by combining the terms. KNN need heavy distance computations to find the closest, which takes much time. We can find a polynomial function that best represents the data instead of a single line. Like in the figure, we can add budget squared and budget cubed terms and find additional coefficients like beta 2 and beta 3. The resulting algorithm is still a linear regression since the outcome y is still a linear combination of the features. We must remember that a higher polynomial function can represent the data accurately, but will likely overfit it. Now that is all I prepared for today. Thank you for listening, and see you in the next video. Bye.